So here are here is the test we went over today. I'm going to start the back and work forward, uh, just because we already went through the first part. All right, so this one here, question, you refer to these molecules. So the molecule with one double bond, so you have to draw a dot diagram. So you're going to have carbon dioxide looks like this. And water looks like this. CH4 looks like this. Forgot to put the 2 electrons here and the 2 electrons there in water. C2H4 looks like this. And pH3 looks like this. All right, so the molecule with one double bond, that would be C2H4. So that's D. And the molecule with the largest dipole moment, it'd be the one that's most polar, so we know that that one's out. And we know that this one's out, because both those would be nonpolar, and this one's out. So this one and this one are polar. However, this one has OH and this has pH, and there's more electronegativity difference between OH than there is P and H. So the answer is water. So that is B. And then the last one, the trigonal pyramidal, that'd be the pH3, because it's a pyramid with that pair of electrons forces it down into a pyramid. So that would be E. Up here, paramagnetic means having unpaired electrons. So if you look at the electron configurations of these, you know that calcium ends in 4s2. I'm just going to put the last part, so it's whatever to whatever 4s2. Vanadium is 4s2 followed by 3d2. No, 3d3, because this is in spot number 23. So 3d3. Zinc is going to end in 4s2, then 3d10. Oh, let's do cobalt. So cobalt is 4s2, 3d7. Oops. Okay, I'm losing track of these. So it's calcium. This is vanadium. This is cobalt. Zinc is 4s2, 3d10. And arsenic is 4s2, 3d10, 4p3. So paramagnetism means that you have unpaired electrons. So you know calcium is out. It's not going to be part of the answer. We know the vanadium's in, because if you have the 5 d orbitals, if it's d3, you got 1, 2, 3. So vanadium is paramagnetic, so I'm going to put a check mark on that one. Check. Cobalt is a d7, so if you go to a d7, there's 5, 6, 7. So you've got 3 unpaired electrons, so cobalt also is paramagnetic. So you got vanadium, you got cobalt. Zinc is not going to be paramagnetic because it's got a full d sublevel, so that's out. And arsenic, since it ends in P3, will be paramagnetic because it's going to have 3 electrons in the P sublevel, like that. So that's a yes. So the answer is vanadium, cobalt, and arsenic. Vanadium, cobalt, and arsenic. So the answer is D. All right, if you draw SO3, if I can draw over here or not, nope, can't do that. If I draw SO3, you're going to draw it like this. So you'd have that, you'd have this, you'd have this. And then you've got 24 valence electrons, so you're going to have 6, 6, 6. You're going to have a double bond. Okay, so this is one way to draw it, and this is an acceptable way to draw it. If you look it up on the internet, you'll find that it shows up like this. It has the 3 triple bonds, or excuse me, double bonds. And the reason that they draw it like this is because this is a minimized minimized formal charge situation. So if you look at the formal charge on this picture, you've got 6 minus 1, 2, 3, 4. So you got a positive 2 formal charge. If you look at the formal charge here, you got 6 minus 1, 2, 3, 4, 5, 6. it's a zero formal charge situation. But either way, the geometry is the same. It's a trigonal planar molecule because it's flat and in a plane. So the answer is A. Number 68, in which of the following processes are covalent bonds broken? Well, if you go from solid to a gas, you're breaking attractions between molecules, but you're not breaking any covalent bonds because they're still I2s. Same thing here. The CO2 is still CO2. If you melt, this is not covalent, so that's out. That's ionic because metal, non-metal. So you are breaking ionic bonds, but not covalent bonds. So we're down to this, but iron's a metal. So really we're talking about breaking covalent bonds when we change diamond from solid to gas. So you remember diamonds have all that, the network covalent bonds that never stopped. It was one big macromolecule, right, Avery? You remember that? Diamond's a big network covalent, so the bonds never stop.
Yep,
I mean, the molecule never stops. This is one big old molecule.
It's a really hard break.
But if you gasify it, then you have to break those bonds because these are carbon atoms floating around as a gas. So the answer is D. That's the one where the covalent bonds are broken. All right, now this is a question that's kind of about bonding. It's about vapor pressure. So on a mountaintop, it's observed that water boils at 90 and not at 100. On the mountaintop, well, boiling happens. Here's a little picture. And if you have water, this is a picture of water here, a beaker of water. Inside there you have water molecules pushing on each other. They're moving around, they push on each other. When they push on each other as hard as the air is pushing on the surface, then they form little bubbles and boil. So if the air didn't push as hard on the surface, then the water would be able to boil at a lower temperature. It wouldn't take they wouldn't have to push on each other as hard to match the air pushing on the surface. So once again, boiling happens when these molecules push on each other as hard as the air pushes on the surface. So if the air is not pushing as hard on the surface, then the molecules don't have to push on each other as hard to boil, so the boiling point will be lower. So best answer has to do with lower atmospheric pressure. Okay, so this so an equilibrium water vapor pressure is higher due to the higher atmospheric pressure. No. The equilibrium water vapor pressure is lower due to the higher atmospheric pressure. No. The equilibrium water vapor pressure equals the atmospheric pressure at a lower temperature. There's your answer. Because these don't have to be as hot to push on each other as hard as the atmosphere pushes on the surface. Okay, on this one, which has the largest dipole moment, which one has hydrogen bonding? Remember, hydrogen bonding is set up when hydrogen is bonded to a highly electronegative element, not another one. Okay, so far I've drawn 2 molecules, now 3 molecules of HF. Valence electrons, the rest of the electrons in the dot diagram go there. Have I drawn the hydrogen bond yet? No. So the hydrogen bond is, oops, that was kind of neat, but I did it in the wrong way. It's right there. Let's do this. Okay, hydrogen bond exists between the molecules. Here's another one right. How did I do that? Right here. Darn it. Backwards again. All right, one more time. So the hydrogen bond is right. I gotta quit playing with these toys. The hydrogen bond is right there. Oops. Is right there. My arrow's not doing so well. All right. One more and we'll stop this section of the video. All right. Types of hybridization by the carbon atoms in propene include which of the following? So let's draw propene. Remember, propene would have a C double bond because it's an alkene, not an alkane. Remember back to the organic chemistry. And it would look like this. These lines are hydrogen, so 3, 1, 2. So there's the 2 right here. I drew it back upside down. Here's 1. That's this one, and then these 3. All right, so what kind of hybridization is there here? That would be both those carbons I just highlighted would be sp2, wouldn't they? 3 domains, sp2, 4 domains. So sp2 and sp3 both. So 2 and 3. The answer is D. All right. I'll stop there, and we'll continue on the next video.